So in the last video we saw that we needed to know a boundary condition or initial position in order to be able to find the position of an object with time given its velocity. But there is one other way we can get around this. In a particular physics problem we may not be interested in the new position. What might really matter is the displacement over a period of time. So we might just be interested in how far an object is moved, in which case we don't actually need to know the original position. If we do a quick example of this, then we could say our displacement, our position, is the integral of the velocity with respect to time. Now let's suppose that v equals t squared. Then we could integrate this. Let's suppose that I am just interested in how far the object has moved between two times, the time t equals a and the time t equals b. Well, I could actually just substitute this in twice. So I could just figure out what is the position at time equals a. So in that particular case, I would get x at time a is equal to 1 over 3 a cubed plus c. And I could do the same thing for b. Now if I just want to know how far I've moved, the change in position, I can just subtract these from each other. So my change in position is equal to x of b minus x of a, which is, now in this particular case I've got a plus c and a minus c, so they will cancel each other out, and so I'll simply be left with 1/3 b cubed minus 1/3 a cubed. So this is the idea of what we call a limit of integration. So this is where we don't have the boundary conditions in terms of we know where you start at a particular point, but instead we just say we're interested in the difference in position between 2 points in time. So the way that we represent those, if we wanted to know how far you've moved displacement x between time a and b, we add the limits like this. So this is telling us to evaluate the velocity at b and subtract the velocity at a, and that will get rid of our factor of plus c that we would normally be stuck with. If we look at this more generally, then what we can say is that the displacement or the change in position is equal to the integral of the velocity over time between two times, t equals b and t equals a. Just to show you how we do the notation in all our working, let's suppose that this time we're going to let v equal t, so that means when I integrate, half of t squared. But then we evaluate this at b and subtract off a. So this is the notation that we use, signifying that we still need to substitute in b and a. So that would be equal to, in this case, half b squared minus half a squared. So to summarize the key new relationships that you need to take away from this week, there are all sorts of integrals that we can do in physics, but the key one that we're going to be looking at this week is the change in position, or the displacement, is the integral of the velocity with respect to time, and the change in velocity is the integral of acceleration with respect to time, and we may put limits on those in order that we can just know the change rather than looking for a specific value.